Today, we are going on a journey, a deep dive, and I mean literally, to solve a huge mystery that's right under our feet. It's a scientific detective story, and we're hunting for the secrets at the very center of our planet.
So here's the big question, right? This is the central puzzle for geologists. How do we know what's inside a planet that we can't possibly explore? I mean, think about it. We can send probes to the farthest corners of our solar system, but Earth's own interior? It's completely off limits. It's way too hot, the pressure is just crushing. Honestly, it's more hostile down there than deep space.
And to put that into perspective for you, the distance from where you are right now to the center of the Earth is over 6,000 kilometers. That's just a mind-boggling distance. And with all of our amazing technology, we've barely even scratched the surface.
Okay, so if we can't go there, if we can't send a camera down, how in the world do scientists piece together what's going on in this massive hidden realm? Well, it turns out the answer isn't about digging deeper. It's about being a detective.
And just like in any good detective story, the whole investigation kicks off by gathering all the evidence you can find. And for scientists studying the Earth, that evidence falls into two main categories.
You've got what we call direct clues. That's the stuff we can actually get our hands on and touch. But then there are the indirect clues. And this is where the really clever detective work comes in, because this is how we learned the big secrets.
So direct clues are pretty straightforward. We're talking about rocks brought up from mines, samples drilled from the deep sea floor, and of course, the molten rock, magma, that spews out of volcanoes. It's all incredibly valuable stuff, but here's the thing. It only gives us a tiny peek at the very, very outermost layer of our planet.
And how deep is that peak? Well, the deepest hole humanity has ever drilled is the Kola Super Deep Borehole, and it only went down about 12 kilometers. Now, that's an amazing engineering achievement for sure, but it's a tiny, tiny fraction of the way to the center. It's barely a scratch.
So, to really see what's going on deeper down, we need to get clever. We need indirect clues. And scientists have a whole toolkit for this. They study the makeup of meteors, they look at tiny changes in gravity and the Earth's magnetic field. But the smoking gun, the one piece of evidence that really cracked this case wide open, it came from listening to earthquakes.
Yeah, you heard that right. The breakthrough came from listening to the planet, specifically by studying the incredible vibrations that travel right through the Earth after an earthquake.
These vibrations are called body waves. Why? Well, because they travel through the entire body of the Earth. You can almost think of it like a giant planetary-scale ultrasound. As these waves zip through the planet, they change their speed, and they even change direction, all depending on what kind of material they're passing through.
Now, here's where it gets really interesting. There are two main types of these body waves, P waves and S waves, and they behave very, very differently. Understanding that difference? Well, that's the key to this whole detective story.
Okay, so P waves, or primary waves, they're the fast ones. They can travel through pretty much anything. Solids, liquids, gases, you name it. But S waves, the secondary waves, are slower. And, more importantly, they have a critical weakness. And this is so important. S waves cannot pass through liquids. At all. It's like they hit a brick wall.
And that one little fact about S waves, that became the key that unlocked the entire mystery. It's the reason scientists were able to make a truly startling discovery about what's deep inside our planet.
See, scientists started noticing something weird. On the opposite side of the planet from a big earthquake, there was this huge area, this shadow zone, where the S waves just never showed up. The P waves would arrive just fine, but the S waves? Gone. Vanished.
So what gives? What could possibly block the S waves but let the P waves pass right through? Well, there's only one possible explanation. The existence of that S-wave shadow zone meant that a huge part of the Earth's deep interior had to be liquid.
And just like that, the case was cracked. This seismic evidence was the proof they needed. It showed that the Earth isn't just one solid ball of rock. Nope, it's made of distinct layers, a world within a world.
So let's break it down. We live on the crust. It's the thin, brittle, outermost layer. And when I say thin, I mean it's incredibly thin compared to everything else, kind of like the skin on an apple.
Then you go deeper and you hit the mantle. This is a massive layer of solid rock, but the upper part is so hot that it can actually flow super slowly over millions of years. This part is called the asthenosphere, and that's where we get magma.
And then, right at the very center, you find the core. This is the super dense heart of the planet.
And this, my friends, is the solution to our whole mystery. This is what was stopping those S-waves.
But wait, there's more. The seismic data shows the core actually has two parts. There's a liquid outer core, that's the S-wave shadow zone we were talking about, and then there's a solid inner core. Now, you might think, how can it be solid if it's even hotter? Well, the pressure is just so immense that it squeezes the metal atoms back into a solid state. And all this is made of mostly nickel and iron.
So, understanding this inner structure isn't just some cool trivia. It's absolutely crucial, because the processes happening deep, deep inside the Earth are what shape the world we see right on the surface.
And you know, the most dramatic example of this? Volcanoes. They're basically windows into the mantle. It's where all that pent-up heat and molten rock from deep below finally finds a way to escape to the surface.
But what's really cool is that sometimes the magma doesn't quite make it all the way. It pushes up into cracks in the crust, but then it cools down before it reaches the surface. It solidifies into these amazing underground shapes, like walls called dikes or sheets called sills.
So there you have it. By cleverly listening to the echoes of earthquakes, we solve the mystery of what's inside our own planet. We discovered this incredible dynamic engine that's constantly at work. And it really makes you think, doesn't it? Our planet's interior built the world we know. What on earth will it create next?